So proceeding this morning, drawing in the same talks a little more contrast and complementarity between the two approaches. Our next speaker is Dean Follmann. Dean graduated from Carnegie Mellon University with a PhD in statistics and joined the NIH in 1988 and spent 14 years at the NHLBI, where he was involved in the design and analysis of multi-center clinical trials. Joined the National Institute of Allergy and Infectious Diseases as the head in 2002 and expanded the biostatistics research branch. His current interests are broad, including counterfactual models, HIV vaccine development, crossover trials for survival endpoints, interesting, bivariate mixture models, and correlation in clinical trials. And Dean's topic this morning is strengths and weaknesses of clinical trials and observational studies. Dean?
Well, thank you for the nice introduction, John. I'd like to thank the organizers for inviting me to come here. I've had a very interesting day so far and yesterday, and I learned a lot of things about trials I hadn't known. So I found it very useful so far, and I hope the day continues that way. So I'll be talking about strengths and weaknesses of clinical trials and observational studies. And I have no potential conflicts of interest. I work for the NIH, so I can't really take money or anything from outside sources. So when I was growing up in the Midwest, I was quite interested in reading books. And one of the authors I liked a lot was Sinclair Lewis, who, in my mind, really understood the Midwest sensibilities. He wrote in the 1920s, and yet what he wrote struck true to me when I was reading it in the 60s and 70s. One of the books that I quite liked was called Aerosmith, which is a story about a doctor who's singularly devoted to the experimental design. He's interested in improving public health, and he's a great scientist in my mind. He had a mentor called Max Gottlieb, and when Aerosmith found that he had a compound which seemed to destroy bacteria in the test tube, his mentor told him that he needed to test it in the field. As it turned out, there was a plague raging in a Caribbean island, and so this was a great opportunity for Dr. Aerosmith to go test his new compound, which he called phage. So he understood from Max's tutelage that he needed to be dispassionate in how he assigned treatment, and so he gave half of certain districts phage and the other half got nothing. And so he was all planning on going forward to this, and he steeled himself because he knew that many people would be begging for this treatment, even though it was unproven. But he knew that if he was going to get a reliable answer that would stand the test of time, he needed to adhere to the experiment. Well, in this fictional story, unfortunately, his wife got the plague and died, and he became despondent. The experiment was ruined, and he went back to his institute in New York, unclear what to do. Well, the institute director had gotten wind of what an interesting experiment was going on there, and there was great fanfare with the press and so on. And so he was pressured to produce a glorious result, which he ended up caving in and doing. So this is what I read in the 60s, and I thought, proper experiments had been done in medicine since like the 1880s or something. And when I came to the NIH, I was surprised when Janet Wittes told me that the randomized trial was basically a relatively new invention from the 50s, and it was caught on quite a lot. But anyway, I was interested to find out to come to NIH and see what the truth was. So anyway, there are certain things you can learn even from this fictional account. Importantly, it's key to really have randomized assignment or a dispassionate assignment of the treatment or the control to the different groups. It's important to maintain your experiment. Even if your wife dies, what's important, you should try and honor the experiment and continue with it. The data that he ended up getting was essentially observational study, and it ended up that pretty much everyone got the phage, and so he was left with trying to dissect trends of the attack rate or the death rate before and after districts and people got phage, and the results were, according to the biometrician in the story, not very impressive. And yet also the pressure to produce appealing results is kind of timeless. We still understand that today. So let's move forward to the 2010s where we are now and talk about randomized trials and observational studies. So I think it's understood randomized trials are great. They're the perfect instrument, the royalty, the gold standard if you can pull one off. But they have certain drawbacks that we would all recognize. They can be expensive in time, in terms of informed consent. It seems to be there's a greater and greater regulatory burden for us to conduct these studies, and that gets old and expensive. Another concern is that has been raised that they are restrictive. You try and identify patients who are most likely to benefit from the treatment. Being a good experimentalist, that's the sharpest instrument for you to detect a benefit of treatment. But if you do that, generalization to the broad population that will be using the therapy might be more of a leap. Another criticism that's been leveled by observationalists, I would say, is that long trials of chronic diseases, it's nigh impossible to have patients adhere to their therapy over years and years of follow-up, at least perfectly adhere to the therapy. And so the arms become polluted, and you're not really answering a causal question of what's the effect of pure adherence to this treatment versus nothing over a long period of time. Everyone recognizes that observational studies have biases, but they can have some attractive features as well. They can be much less costly. They can be quite inclusive, and therefore generalization of the results can be easier. And I think probably most importantly is that there's this view that modern statistical methods can fix the bias. And there's been a lot of work done in this area, principally, to my knowledge, by Jamie Robbins and people who work with him, who are quite passionate and quite persuasive, I would say, to many people about the role of observational studies in the context of modern statistical methods. So I want to talk briefly about the randomized trial, and then I'll spend a bit more time about observational studies. It's not, the reason I'm going to spend relatively little time about the randomized trial is because I think it's relatively simple. Randomization, I think, is a beautiful thing. If you randomize people to treatment or control, you know that probabilistically they're going to be similar in terms of everything that you can measure and everything you can't measure. So it's a great tool. And so any differences that you see in outcome during the course of follow-up can be assigned to the treatment assignment. And if they adhere to the treatment, you can causally assign it to the treatment itself. And I unabashedly think it's the greatest medical invention ever. I wonder where we would be in medicine if we didn't use this tool in so many ways for so many questions. And so once you randomize, I think everything is easy as long as you respect and honor randomization throughout the conduct of the study and the analysis as well. So for a statistician, you can do a very simple analysis that gets you a good answer for a randomized study. You can just calculate the average response in one group, calculate it in the other group, and subtract one from the other. And this will give you a good estimate of the treatment effect that's unbiased. Things are different with observational studies, and we understand that the decision and really the agreement to continue taking the drug depends on many factors. These could include patient characteristics, doctor characteristics, sort of the milieu in which you work in, or your doctor works in, or what he's read recently, or who's visited him lately, and also things that you can't collect or can't even quantify. Now, observational studies, I think, have had a role in medicine for a long time. They've been used to identify risk factors, which lead to hypotheses which can be tested with interventions. And I think we all agree that observational studies can reliably detect sort of large effects. And I give a couple examples here: smoking and lung cancer, and also combination antiretroviral therapy for HIV, which had a Lazarus-like effect, I would say, in rescuing people who were at death's door. And when it came out, there was a huge turnaround in the prognosis for people with HIV. The issue, I think, at hand here at this conference is really the role of observational studies in testing or settling questions where you have modest effects. So for randomized trials, I said the key requirement was randomization. I would say for observational studies, it's recognized that the key requirement is what they call to have no unmeasured confounders. And so just to briefly review what I mean by a confounder, it's some characteristic which could be measurable or not that impacts both your outcome and your chance of getting the treatment. So for example, ejection fraction. Perhaps if you have a bad ejection fraction, you're likely to have a bad outcome, and you might be more likely to get the treatment because maybe the doctor is more likely to prescribe it for you, or maybe with knowledge of the bad ejection fraction, you're more likely to adhere to the drug over a long period of time. So that's a confounder. And how do observationalists deal with this? Well, the approach is to create groupings of patients who have similar characteristics in terms of necessarily what we can measure. So for example, we'll say, or on the basis of data and investigation, you might look at people who are old and have ejection fractions between 0.2 and 0.3 as saying these are similar characteristics of patients. Or even more finely, we can say let's consider people who have a specific ejection fraction. And the key requirement in terms of no unmeasured confounders, I think you can simply state, is within these subgroupings, where we drill down far enough, the treatment assignment is like that of a randomized trial. And once you have a randomized trial, everything is simple. You can make causal conclusions, you can get strong inference, but you have to be able to, on the basis of data, drill down and find out and uncover essentially a randomized trial. So I want to give two brief examples of ways that you can try and achieve this. So the first one is regression analysis, and here I've got a scatter plot of made-up data. On the y-axis I have quality of life, and on the x-axis I have ejection fraction here. These green dots are people who were assigned treatment. I know their ejection fraction, I know their quality of life, I can calculate their sample average, and it's a little less than 80. Similarly, for the control group, which have these red dots here, I can make the scatter plot, average all the quality of life for people who have got the control, and I look at the quality of life here. It's a bit bigger. So if I just do a naive, simple analysis that said I'm going to take the sample average of each group, I get what's a biased estimate of treatment effect. So this regression adjustment, along with the assumption of no unmeasured confounders, does the following. It postulates a smooth relationship. I've drawn a linear regression here. It could be anything as long as I specify it and I can estimate it. And I look at the difference in these regression lines, and I note that, in fact, when I adjust for the ejection fraction, there's nothing going on. And to make a causal conclusion that the treatment effect really is useless, I have to make this assumption that down here for these different ejection fractions, like over here, the probability of getting control is like that of a randomized trial, with probability 2/3 of getting control and 1/3 getting treatment. Over here, it's the opposite. This is made-up data just to illustrate the point. This is one of the techniques people will use to try and draw causal conclusions from observational studies. The other method I want to talk about briefly is a little less finely drilled down. So here I'm looking at groupings of patients instead of looking at specific ejection fractions and thinking ejection fraction, if I get that right, it's like a trial. Here I'm looking at these post hoc created groupings based on data, sometimes called propensity scores, where I will look at, say, the old people who have, let's say, a poor ejection fraction. I'll note that within this grouping, about 3/4 of the people get treatment. And in this other grouping here, about 1/4 of the people get treatment. Maybe they're healthier, the doctor thinks they don't need treatment so much, and there you have it. So I made up some data here for a very small trial. I like big trials, but this was easy to put on the slide. I have three people in this stratum who got the treatment. These are their quality of life scores. One person who got control, here's their quality of life score, not much going on. Similarly, in contrast here in the other grouping, control group is more common than treatment. When I just add up the treatment people and subtract and take their average and subtract off the control people, I see a very harmful effect of treatment. And the problem is it's because healthy people are tending not to get treatment, sick people are tending to get treatment. So how can we adjust for this? Well, there's a method called inverse probability weighting, which I like to think of as clones, and sometimes it's called that in the literature, where they'll have clones or ghosts, where a patient who's underrepresented is counted multiple times. So here's Homer in the cloning machine. I don't know if you saw that Simpsons episode, where he steps through the machine and many homers are made. So the idea here is, in this stratum where control people were underrepresented, I'm going to have this one person here counted 2 more times, and now I have like a 50-50 trial here. Same thing here in this grouping where I had 1 person on treatment, 3 in control, I'm going to count this person twice. And so now I have a 50-50 randomized trial here, essentially. And when I take the inverse probability weighted treatment effect estimate, adding up the real numbers and the counting of this other person 2 more times and so on, where in this artificial example where nothing is going on, I properly estimate essentially no effective treatment. So this is the other way you can try and uncover a randomized trial. Drill down, find out where treatment assignment is as if it's randomized, and then analyze accordingly. And so that sort of presupposes or has the view that you can uncover a randomized trial. But there might be unmeasured confounding. Just for completeness, I want to go through this. And so I talked about old people who had poor ejection fractions, but it could be that within this there's this intangible quality, say optimism or pessimism, or something like that, where optimistic people are more likely to use the drug, they're more empowered, they think they can control their destiny, and they might have better outcomes. Whereas pessimistic people are the opposite. They're less inclined to think treatment's going to help, and they're likely to have worse outcomes. And so if we don't know this, or we cannot measure it, we can't control for it in the analysis. And so what we'll get, thinking we've done all we can, is to look at this grouping of old and poor ejection fraction, and we'll see that there's a treatment effect going on here. There's a benefit of treatment. Whereas if we drill down, the optimistic people have a slightly higher probability of treatment, and optimistic people have good quality of life, but it doesn't matter if you're on drug or not. And pessimistic people, there's less likely to take treatment, and they also have poor outcomes, but once again, there's no effective treatment. And the big problem, and I think where the schism lies between people who do trials and like observational studies, is whether you believe you've got the unmeasured confounders all measured. And this is something I would say we can't really know. It depends on your judgment or your belief. Are you comfortable making that assumption, or are you not? And I think that's the essential difference between these two camps. You can do sensible adjustment. You can use all your knowledge to bear on this problem. You can do sensitivity analysis. And that's some of the modern techniques that people use to try and buttress the observational analyses. But still, it's something you have to believe or assume or feel comfortable with. So everyone talked about the coronary drug project, and here it is yet again. This is a classic study conducted in the 1960s, and so if we think of getting drug as like being treatment, where it's green here, and not getting drug is like being on the control, we see this big difference in death rates. There was in the paper by Cannon in the New England Journal, they did baseline adjustment, as was mentioned, and there's this very slight difference in the death rates. It goes from minus 9.6 to minus 9.4, both whopping treatment effects estimates. Yesterday I learned that the p-value here was a bit smaller than it was here, but still very strong in each case. And as you know, this is a randomized trial, so when you compare the randomized group, there's nothing really going on. And so, you know, you could say without a randomized placebo group, you might have gotten the wrong answer. Now, there's an important comment made yesterday that basically the adjustment that was done for the coronary drug project was for clinical and physiological measurements. And that's what they measured in the 80s, and probably still what they measure nowadays. And so that sort of deals with half of the confounding issue. These variables, physiological measurements, clinical characteristics, would be related to outcome, but they might not and probably aren't related to this more intangible thing of fidelity to treatment. And so if we could turn back time and try and measure, say, fidelity to treatment or personality characteristics in the coronary drug project, it would be an interesting analysis to do. Another thing you could think of doing really is to have a run-in period, say, for 1 month before you do the coronary drug project and look at adherence during that pre-randomization period as a way to try and get at a confounder of fidelity to treatment. Of course, you could always say if you're going to do that, you would just randomize people who had good fidelity, sharpen that clinical trial instrument, and those people who are most likely to comply. Another example that was talked a lot about yesterday was the Women's Health Initiative, mostly focused on coronary cardiovascular disease. Here I'm going to be talking about the effect of estrogen on breast cancer. So Ross Prentice did a study, I think it was in epidemiology, where he noted that in the observational study, the hazard ratio for breast cancer was about a 30% increase, and in the clinical trial, there was a 30% decrease. These are different, statistically different. And when he adjusts for screening, estradiol, and time for menopause to estrogen initiation, this difference kind of goes away. So there are situations where, with adjustment in the observational study, you can get close to the result that you get in a randomized trial. Now, in some ways, you have an advantage if you're an observationalist looking at trying to explain away the result. You know what the treatment effect was in the randomized trial, and so you kind of know where you want to go. Doesn't mean you're devious or misleading or anything necessarily, but you do have kind of an advantage, I guess, that is something to be aware of. An example closer to my home, where I work now at the National Institute of Allergy and Infectious Disease, is a central question for HIV treatment, which is when to start antiretroviral therapies. The pendulum has swung back and forth on this over the time since CART was initiated or became popular in the mid-90s. And a few years ago, there was an important observational study called NA for North America, Accord for, I guess, the collection of people working on it, where this is a study where they try to use modern causal methods to mimic a clinical trial of immediate versus deferred ART in HIV-infected patients. And the basic method that they used there was inverse probability weighting. It was a very complicated statistical model, actually. And one of the advantages, I would say, of inverse probability weighting is that even if you have a complicated model, you just weight people differently within the model. So that makes you have entree to a wide variety of statistical methods. Anyway, for people who had baseline CD4 counts of 350 to 500, there was about a 70% increase in the risk of death for delaying. And for baseline CD4 counts greater than 500, there's nearly doubling in the risk of death for waiting. But this was not convincing, really, to my institute, and we funded an ongoing study called the START trial, which is a randomized trial of about 4,000 people with CD4 counts greater than 500, and the question is immediate versus deferred therapy for those people. The study is ongoing. This is going to be different, though. Importantly, this study looked at all-cause mortality. This study is going to look at mortality plus serious AIDS and non-AIDS events. So I wanted to talk about the different methodologies, give some examples of where they seem to work well and not. And I think we all understand that certain settings are relevant or important for a randomized clinical trial. Other settings call for an observational study, and the real issue is, what do we do with the gray areas? And how do we decide what study to do? And this boils down to sort of arguments in rooms or controversies between people, and who wins these arguments? Well, maybe it's the best debater. Maybe not the person with the best argument, but maybe the person who's the best arguer. We tend to fall into tribes, I would say, in terms of whether our fidelity to a randomized trial or an observational study, and it's really hard to get beyond that. And I kind of don't like that. I feel I'm in one tribe, but I also feel like we should try and give it a fair shake, and for each question, try and look at what is the best method or the best tool for that question. And so one way you could try and help yourself with this is some kind of analysis where you try and lay things out. So I just dashed out something here that I think would be helpful, be hard to do, but in trying to decide for a specific question in a gray area, what should you do, an observational study or randomized trial? So you could imagine making a table where the state of reality is either the treatment works or a treatment doesn't work. You don't know what it is, but if you know if the treatment works and it has a delta of, say, 30% reduction in mortality, maybe you would save 10,000 lives when you rolled it out, and it might cost $4 million. And you can fill up the rest of the table in a similar way. Then you could also think of the treatment action. And so let's suppose treatment work, and if we're doing a randomized trial that's properly powered at 90%, we'll have probability 0.9 of making the right action or decision if we do the trial, and probability 0.10 of making the wrong action. So these are easy to fill out. The black things are easy to fill out because they're how we design trials anyway. It's a bit harder to fill out these probabilities for observational studies. But still, I think it's an interesting exercise to try and do. So anyway, you can fill out this table. If treatment is useless with a randomized trial, we'll conclude that about 5% of the time, the opposite 95% of the trial. I made up some numbers here for what might happen with an observational study. And then you can kind of bring it all together with an expected result and maybe have a more informed decision about what to do using a table like this. This table, importantly, doesn't have the cost of the trial or the observational study on it, and so that would be another consideration. And I'm really thinking more of the arena where, which was discussed yesterday, maybe at the VA, where they come together, they have limited resources, they have questions to answer to try and improve the health of the veterans, and so they'll decide on a case-by-case basis, what are we going to do with the money that we have to try and improve their health? So I thought it was nice. So the future. I went to school at Carnegie Mellon, and at that school there was a group of Bayesian statisticians who were, I would say, in the minority of the spectrum of statistical theory at the time. And yet they were quite passionate, they were quite persuasive, and they didn't get up. And I would say that their influence is being felt more and more in statistics. And I see something kind of similar, I would say, in the clinical trial and observational study world, where the adherents to the observational methods are young, bright, passionate, and they got a lot of get up and go. And so I don't know what the future has. I know that change comes basically when old people die off. It's not because you change someone's opinion. It's because your generation goes away. So anyway, that's a sobering thought, I think, perhaps for clinical trialists. You know, do nothing and you could be overtaken by the passionate people. So anyway, just the take-home message I want to end with. I think RCTs are great. I think observational studies, we can all agree, will answer questions of large effects readily. And the real issue is what to do about modest effects. And I think at the end of the day, the observational studies have to be clever enough to uncover a clinical trial in some fashion or in some ways to draw the causal conclusion. And whether you think they can, you know, that's possible or not is really, I think, the essential question of whether you like trials or observational studies. I guess the final point I wanted to make is I don't really know if the unmeasured confounders are there or not, and so the only way to look at this empirically, I would say, is to look at different cases of where you have a clinical trial outcome, and then you also have an observational study looking, using modern methods to try and get at a causal kind of conclusion and see did they line up or not. It's not a perfect way to resolve the issue, and in future questions, you know, it won't have been settled or looked at for your particular question, but it's a way to look at it, you know, beyond just tribal allegiance, basically. It's a way to try and look at data. So anyway, that concludes my talk. Here's some references that